and semiconductor. We have 4 talks for about 20 minutes.
And this is going to close at 2 p.m. Yeah. So yeah,
yep.
We have more time. So I'm going to talk on the initial state of the metal and metal interface for resistive switching applications. So since the resistive switching is a new thing, some guys. So first, let's start what is actually resistive switching. So if you're going to start on the electrical, they have a 4-parameter voltage, flux, and current and charge. So if you're going to make a relationship, we got a 3 different circuit, but still they have a one relation between the charge and flux missing until 1971, or in the Dr. Liu Chon, he mathematically derived an equation and formed that maybe there should exist a circuit which is called a memoristor, and is practically prepared in 2008 by HP scientists. So how this actually switching is work? So is the device, if we increase the voltage in a positive direction, the conductivity will increases, and it can keep memory that conductivity. And if you put the reverse bias, it will give you that previous resistance. So we are going to make devices with these properties, but question is why we need these properties. So in a one sentence, this recent semiconductor based technology, it's almost in the theoretical limit up to so we need new mechanisms. So it would be the replacement of these devices, and it can be used for like neuromorphic device designs. So to do this one, I consider my models. My models actually I am considering one titanium oxide layer with one of the metal oxide layer on the top of them to study these properties. I studied this system on the bus using methodology. To do that, this one is giving us a pristine only metal oxide layer with the metal. And this one is I replace one titanium with the aluminum in the titanium oxide layer to see how it changed their conductivity. I also study with study the oxygen vacancy, how it changed the conductivity, but I didn't actually complete on this system, so I just work on this too. So first one, this one is giving us a 2D presentation of the orbital, how the electron localized in which part, in which layer, metal oxide layer or in the metal layer. So this one is showing the pristine one, and this one is showing the with the aluminum doped one. First, if you look on this lattice structure, by doping aluminum, the lattice structure is distorted muchly, but this one almost showing this pristine titanium oxide lattice structure. So in this case, HOMO -1 and HOMO, there was some electron delocalization on the metal part in here, and this one in the LUMO too. But when I dope aluminum, this electron is moved towards the oxide part, and also LUMO, it's also showing the all electron transfer to the LUMO layer. So maybe because of this oxygen, it could introduce a charge transfer in this here. This one is just an orbital showing of these two previous one, as shown in the previous slide. This electron almost localized on the metal part. In the LUMO is metal part with oxide layer, but in this case of a doped system, this electron is localized on the metal part also. And this is some kind of other presentation of previous slide. But when I take a dose, it's showing that this one is for pristine and this one is for with the metal dope. In the pristine, it's showing that there have a overlap between the Fermi. This is the Fermi level. This one occupied on the. There is some metal characteristics, but there are some significant, energy difference in the HOMO -1 and HOMO low energy state. But when I put the aluminum dope, is giving it a more continuous, orbital, occupations, and also the overlapping of the unoccupied by electron is higher than the undoped system. And these two, I optimize by using the electric field towards the Z direction. Z direction means from here is the metal part to the, metal oxide to the metal directions. In that case, I saw that this one in the undoped system, by applying the electric field, it didn't change the energy level that much. But when in this doping system, it increased the occupation of the unoccupied orbitals with the electrons. Excited electron is much more than compared to this one. So from this DOS calculation, I can say that very good. This one is that because of doping, or under the electric field, it changed the occupation number is huge. So doping change can lattice the change significantly, but most important result is that doping helps to increase the conductivity by minimizing the energy gap and increase the occupation number in the higher steady state. So, but I didn't do much work, so there have some feature work to I need to dose the PDOS and dose.
Okay, we thank Jabit for